Hello everyone. Today in this video we'll be discussing the module 2 of 21PHY12, and in this module what we have is the modern physics and quantum mechanics, and under that there are some topics like we'll be studying about the laws, and after that there are some equations and the derivations which we have to know how to solve the derivations, as well as the numericals are there. So in this video we'll be not solving any numericals. We'll be solving that in a separate video. So this just the theoretical video concepts which we'll be discussing. Okay, so if you like this video, hit the like button and don't forget to subscribe to my channel. Okay, so let's get started. Firstly, we have the topic which is blackbody radiation. Okay, so there are 4 laws under it which we'll be discussing now. So basically, what is a black body? A black body is nothing but if there is light here and there is a black body here, black colored body. At that time, whatever the radiation comes from light, that will be absorbed by the black body, and if we heat this black body, the radiations will be emitted here. Okay, so that is known as the black body, which absorbs the entire radiation incident on it and emits all the absorbed radiation when it is heated to a suitable high temperature. Okay, so this is the black body radiation spectrum for different types of black body. Okay, so one is at 6000 kelvin, 3000 kelvin and 2000 kelvin, and as the wavelength increases, the energy increases for a certain amount of time, and after that it decreases. Okay, so based on this observation, there are few laws which we'll be discussing now. It can be observed that the increasing wavelength, first radiation increases, then after its peak value the gradual decrease happens, and in the further increase in wavelength. Okay, so the first one is the Wien's displacement law. Okay, so this law states that the wavelength is corresponds to the maximum intensity, is inversely proportional to the absolute temperature of the black body. Because as the temperature is increasing, we are observing that it gradually decreases. So it's as the wavelength increases, the temperature decreases. So it's inversely proportional. Okay, so Wien showed that the maximum energy of the peak emission is directly proportional to the fifth power of the absolute temperature. Okay, this is also another derivation of the Wien's law. Okay, so this is the more formal representation of the Wien's law. In 1896, Wien obtained the relation between the wavelength and the wavelength of emission and the temperature of the source as this equation. Okay, so what is in this equation? U lambda and delta lambda. Okay, that is equal to, there are two constants, c1 and c2. Okay, c1 lambda power minus 5 e power minus c2 by lambda t, and d lambda is in both sides. Okay, so this is nothing but the energy per unit volume in the range of the wavelength lambda to lambda plus d lambda. C1 and C2 are the constants. So make sure you remember this formula, write it 2 to 3 times, and to remember this formula. Okay. So this is called the Wien's law of energy distribution in the blackbody radiation spectrum. So in the exam they can ask like explain the Wien's law with the formula as well, and what do these terms represent. So you have to write the following thing here. Okay, so the second one is the Rayleigh's Jeans law. Okay, in 1900, Rayleigh derived an equation for the blackbody radiation on the basis of principle of equipartition of energy. Equipartition means what? Dividing into equal parts. Okay, these are known as nodes. And what is the main thing is that it suggests that an average energy kT is assigned to each mode of the vibration. So in each mode of the vibration, kT is assigned like 1 kT, 2 kT, and so on. Okay, so for each node there will be vibrations assigned. The number of nodes vibrations per unit volume whose wavelength is in the range lambda and lambda plus d lambda is given by this equation. Okay, this is a pretty simple equation. 8 pi you already know, d lambda is here, just you have to include lambda power minus 4. So this is the energy per unit volume in the wavelength range lambda and lambda plus d lambda. Okay, so the equation is as follows. We will be modifying the previous equation here. So instead of this one, okay, instead of this one, what we will be writing is this one. Okay, 8 pi lambda power minus 4 d lambda. Okay, so this is the energy per unit volume wavelength in this range according to Rayleigh. Okay, where k is the Boltzmann constant, which is given as this constant value, and according to Rayleigh, energy radiated decreases with the increasing wavelength. Okay. The third one is the Stephen Boltzmann's law. Stephen's law says that the energy radiated by a perfect black body is directly proportional to fourth power of the absolute temperature. Okay, so this is the sigma, which is nothing but the Stephen Boltzmann constant. Okay. Fourth is the Planck's law. In Planck's law, there are four things here, okay, which we need to know. What is there are three things here which we need to know in the Planck's law. Planck assumed that the walls of the experimental blackbody consist of very large number of electrical oscillations. Each oscillator vibrates with its own frequency. So blackbody, see, if this is the blackbody, it has four walls here. Okay, so these four walls, each has its own oscillator, which vibrates with its own frequency. That's the first assumption of Planck's law. Each oscillator has an energy given by the integral multiple of hv. Hv is the Planck's constant into the frequency of vibration, and any integral value is multiplied with it, and that is the what value answer we get. That is the energy with which the oscillator oscillates. Okay, that's the second thing. The third thing is that it may lose or gain energy, and the derived law as means this is the derived law. U lambda d lambda is equal to 8 pi hc by lambda power 5, and here what we have is 1 by e power hv by kt minus 1 d lambda. Okay, this is the Planck's radiation law. Now we have studied three laws. We will be reducing the Planck's law to Wien's law, as well as reduction of Planck's law to Rayleigh's law. Okay, so by using the equation of the Planck's law, we will be reducing it to the Wien's law. Okay, so let's see once what is the Wien's law. How can we derive it using this one? Okay, so first for shorter wavelength, we'll be writing shorter wavelength. V is equal to c by lambda is large, because if the wavelength is shorter, obviously the value of this will be larger. So when V is large, this will be very large because it is the exponential term here. So this will be very much greater than 1. So this is nothing but this only, because subtracting 1 from a very great value is nothing but the same value itself. So this is the value which we get here. What we have did is just that instead of V we have written c by lambda. Okay, so substituting that in the equation 1, which is in the equation of the Planck's constant, so what we get is this one. This value is getting substituted here. Okay, and after that if we simplify it, we'll get it in this form. We'll take this 5 up, and we'll cut out the similar terms here and take the constants as a c1. So after that we'll get this form, and this is nothing but the Wien's law of radiation. Okay, the same we will do for this also. For longer wavelength, this is very small, so if this is small, this is very small, so this can be taken as equal to 1, because anything e power close to 0, very small value is equal to 1. So if we'll do the squares also, the squares can be ignored, because if this is a small value, square of it will be a much more smaller value, right? Because if there is 1 by 2 square, if you do 1 by 4, that's smaller than 1 by 2, right? So like that this is approximately equal to the same value here, so other terms are neglected, and after that rearranging the terms, we get this value here. Substituting that value in the equation 1, we get this value. Okay, after you simplify, you will get the Rayleigh's gene law of radiation. Okay, so these derivations are very important from exam point of view, so make sure you practice them very well. Okay, moving on, we have the dual nature of the matter, de Broglie's hypothesis. Okay, so what does the dual nature of matter mean? Just as light behaves both as wave and particle, de Broglie proposed that even matter should behave as both wave and particle in under certain circumstances. So that is known as the de Broglie's hypothesis. De Broglie's wavelength, how can we derive it? If a particle of mass m is moving with a velocity c, at that time the energy is equal to mc square. Also, Planck's quantum theory, the energy of the quantum frequency V is equal to hv. Equating both, we get mc square is equal to hv. Then V is equal to c by lambda, so lambda is equal to h by mv. Okay, so that's the de Broglie's wavelength, and the de Broglie's wavelength for a free particle in the terms of kinetic energy. So E is equal to mc E is equal to half mv square. Half mv square, if you take mv as p and do p square, at that time it will be divided by 2m, so you will get p square by 2m is equal to E. Okay, so therefore p is equal to root 2 me, and lambda is equal to h by p, and substituting the value of p as this one, you will get h by root 2 me. This is the expression for the de Broglie wavelength. Okay, de Broglie wavelength for an accelerated electron. So if an electron is accelerated with a potential difference v, the work done on the ev, the work done is ev, which is converted to kinetic energy. So ev is equal to half mv square. If p is the momentum of the electron, then p is equal to mv. Squaring on both sides, we get p square is equal to m square v square, and mv square is equal to p square by m. Using it in the equation, what we get is p square by 2m. Okay, like in the half mv square formula, mv square, instead of that, what we are writing is p square by m. At that time, we get ev is equal to p square by 2m. In that case, p is equal to root 2 m ev, and lambda is equal to h by p. So substituting the value of p as this one, we'll get lambda is equal to h by root 2 m e v. Okay. The next is the Heisenberg's uncertainty principle. It states that it is impossible to measure simultaneously both the position and the momentum of the particle accurately. Okay, at the same time, position and the momentum can't be measured accurately according to the Heisenberg's uncertainty principle. Okay. So if delta x and delta p are the uncertainties in the measurement of the position and the momentum, the particle, then the uncertainty is given by delta x into delta px is greater than or equal to h by 4 pi. This is the constant value. Okay. So its application, there are two applications which is very important from exam point of view. So first one is the impossibility of existence of electrons in the atomic nucleus. Okay. So for that, E is equal to mc square. So if there is a rest mass as well as the rest mass is moving with the velocity v, then the total energy is given by m0, which is the mass, and c square here, root of 1 minus v square by c square. V is the velocity of the mass. Okay. So simplifying it, what we get is if you square it in the LHS as well as the RHS, we get this formula. And if p is the momentum of the particle, p is equal to mv, then instead of v, we will be writing v by 1 by root v square minus v square by c square. Then p square is equal to this formula. Multiplying it by c square, what we get is this one, p square c square. Then substituting the value of 2 in 1, p square c square in 1, what we get is, so which is 1, which 1 is this one. So substituting the value of p square c square in this formula, what we get is this one. Okay, like using this one, so we get it as this one, e square minus p square c square is equal to this one, and e square is equal to p square c square plus this one. Okay, means after cancelling out the common terms, which is c square minus v square here also, so we will be remaining with m square c power 4. This is the, and Heisenberg's uncertainty principle states that the position into the momentum is greater than or equal to h by 4 pi. Okay, and the diameter is in the order of 10 power minus 14. If the electron is to exist in the nucleus, the uncertainty in the position must not exceed 10 power minus 14 meter. Okay, so the delta x is less than or equal to 10 power minus 14. The minimum uncertainty in the momentum is, just apply the values here. So what we get is 0.5 into 10 power minus 20 kilogram meter per second. Okay, but considering the minimum uncertainty in the momentum of electron, at that time it should be equal to p. P is nothing but the momentum. So applying the value of p in this formula, p square c square plus this one, so what we get is m naught is equal to where m naught is equal to this one, this is the weight of the, means mass of the electron. And if the electron exists in the nucleus, then its energy must be equal to greater than, apply the values in this formula and calculate, it should be greater than this value. Taking the square root and finding out the answer, we will get 9.4 macro electron volt, mega electron volt. It should be greater than this one. But it is observed that if the electron exists in the nucleus, its energy must be greater than or equal to 9.4. It should be greater than or equal to 9.4. It is experimentally measured that the beta particles ejected from a nucleus during the beta decay have the energies 3 to 4. It is just having 3 to 4, but it is saying that it should be greater than 9.4. So that is a clear contradiction. That means the electrons does not exist inside the nucleus. Okay, that was the application of de Broglie's hypothesis. Okay. Moving on, we have the next topic, wave function. A wave function is nothing but a physical situation in quantum mechanics, which is represented by a function called as wave function. And what is physical significance? It is used in probability density. Okay, so if this is the wave function and associated with the particle, then the square of it is the probability of finding a particle in a unit volume tau. Okay, so if this is the unit volume and there is a particle here, at that time, if this is the probability of finding it, means this is the probability of finding it in the inside the particle tau, and this is nothing but the wave function. Okay, so this is called as probability density, means where we can find out the particle at. Okay, So here are some things which you need to know, like normalization. Normalization means the probability of finding a particle having a wave function psi in a volume d tau is equal to the square of this into d tau. Okay, if it is certain that the particle present then in the finite volume, then it is equal to means 0 to tau, means from 0 area to the tau area, and this is the integration, it should become 1 means because it's existing, right, the particle, we know that for certain. If it's not certain, then the area will be from minus infinity to infinity. Okay, coming to properties of wave function, there are 4 properties which we need to know. The first one is the property that psi is a single valued everywhere. So what does this mean is, if there is a function f of x and if it's single valued everywhere, we can find 3 values f1, f2 and f3 at x is equal to p, and f1 is not equal to f2, which is not equal to f3. But these 3 exist everywhere, so these values should be same, but that cannot be same because these are different values, right? So that's the contradiction here. Okay, so this wave function is not acceptable. The probability of finding the particle has 3 different values at the same location, which is not true. Okay, so the graph will look like this: 3 different values at the same location, this is not possible. Okay, and psi is finite everywhere. This indicates that there is a large probability of finding it, which is against the uncertainty principle, which states that it is having very less probability of finding the electron. Okay, so the second wave function is also not acceptable. The third wave function is nothing but the about the derivative. Here, firstly, what you have to write is it is the second order differential equation, and its first derivative must be continuous at x is equal to q. If you see the graph, it is not continuous actually, so it is also not acceptable. Okay, it is a discontinuous function. The fourth one, for the bound states, psi must vanish at the potential boundary and the outside. If psi star is complex function, then psi star into psi star must also vanish at the potential boundary and the outside. The wave function that satisfies the above 4 properties is called eigenfunctions. Okay, so if they ask about the properties, you have to write these 4 properties and explain. Okay, moving on, we have the next topic, which is time independent Schrodinger wave equation. Here there is the derivation. Okay, so consider a particle of mass m moving with velocity v. Okay, the de Broglie wavelength is lambda is nothing but h by mv, and mv is nothing but momentum, so it is h by p. Okay, and the wave equation is psi is equal to a e power I into kx minus wt. Okay, remember this one. A is a constant and w is the angular frequency of the wave. Okay, this is the equation which we will be using. Then differentiating 2 with respect to t. Let's differentiate this with respect to t. Double differentiate and get this value here. And the equation of a traveling wave is d square y by dx square is equal to 1 by v square d square y by dt square. This is a standard one. Okay, in the same way we have for the psi value also, it will be nothing but d square psi by dx square is equal to 1 by v square d square psi by dt square. Okay, so by those two equations we get d square psi by dx square is equal to minus omega square by v square into psi. Okay, and substituting the values of the omega as 2 pi v and v as u into lambda, at that time what we get is this equation. Okay, this equation, and from that we have to just calculate what is 1 by lambda, which is equal to this one. And kinetic energy is half mv square, so we have half mv square here, p square by 2m, which is equal to h by 2m lambda square. So here in the denominator there is 1 by lambda square, so substitute this value here. Okay, so what we get is k is equal to h square by 2m. We have just substituted that value, and we get this equation here. Simplifying that and calculating the total energy, total energy is equal to ke plus pe. Kinetic energy we have calculated now, half mv square, and p is this one. So E minus v is equal to this one, and we are just calculating what is value of d square psi by dx square, and taking the other terms in this side we get this equation. Take this term here, and what you get is this equation here. Okay, this is very important one. So this is the derivation of the time independent Schrodinger wave equation. Okay, before moving on further, let's quickly revise what is eigenfunction and eigenvalues. Eigenfunctions are those wave functions of quantum mechanics which possess the properties of that they are single valued, finite everywhere. Also, the first derivatives are continuous. What are eigenvalues? It's possible eigenvalues are the possible values of the physical quantity like momentum, energy, etc. of a system that are observed within the eigenfunctions. Okay, are operated in the quantum mechanics operators. So that is, if there is an operator A here operating on the well-behaved function psi, produce back the wave function multiplied by a constant factor. Okay. So here the psi is called the eigenfunction and lambda is called the eigenvalue. This is the eigen function. This is the function. This is the value. Okay, and A is associated with the eigenfunction psi. Okay. Let's see what are the application of Schrodinger wave equation. This is also very important from exam point of view. So there are some cases here like the types of application. Okay, so the first one is energy eigenvalues for a particle in one dimensional infinite potential well. Okay, so if you get this type of to describe this particular equation, application of Schrodinger wave equation, that time you have to draw this one. Okay, so first make two lines here, and here v is equal to 0, v is equal to infinity, v is equal to infinity. This is the like a container. Okay, and x is equal to 0 till x is equal to a, and the particle lies here. Okay, after making this one, write these things. Consider a particle of mass m free to move in one dimension along the positive x direction between x is equal to 0 to x is equal to a. The potential energy outside this region is infinite, and within the region it is 0. Okay, so that's what we have mentioned here. Inside this region it is 0, outside it is infinite. And after that, such a configuration of potential in space is called infinite potential well. Okay, so Schrodinger wave equation outside the well is, here it is E minus V, so V is infinite, so it is infinite here. And for outside, the equation holds good if psi is equal to 0 and psi square is equal to 0. The particle cannot be found outside the wells and also at the walls. The Schrodinger wave equation inside the well is, here it will be like E minus V, so V is 0, so it will be just E here. So rearranging this, what we get is the same thing here plus a k square psi. Why k square? We are taking this whole term as k square. So when we get this equation and we solve it, what we get is this one, and after that finding out the values of c at x is equal to 0 and psi is equal to 0, we get the value of c here. In the same way we get the value of d as well, and after that if we substitute the values of k, we will get k is equal to n pi by a, and equation 5 and 6, in substituting equation 5 and 6, which is this equation, and this equation in 4 is which one? This equation. Okay, substituting the values of c, d and k here, so what we obtain is this equation. Okay, this is the equation which we will obtain. And after that we'll be considering from n is equal to 0, n is the energy levels, so we'll start from 0. When n is 0, it is not acceptable inside the well because psi of n is 0. It means that the electron is not present inside the well, which is not true. Okay, thus the lowest energy value for n is equal to 1 is called the 0 point energy value or the ground state energy. It starts from 1. Okay, so at 0 point it is h square by 8 ma square. Okay, if we put here 1, at that time what we get is h square by 8 ma square. Okay, that is the energy. The states for which n is greater than 1 are called excited states. Okay, and to find out the value of d, normalization of the wave function is to be done. So what is the formula for d here? This is sigma psi square 0 to a, it is equal to 1. Okay, now this value what we got is d square sine square n by n pi by a. Okay, and n pi by a into x. So integrating it, taking d square outside and integrating and simplifying, applying the limits, what you get is d is equal to root 2 by a. Okay, so substitute d in the equation 7, what you get is this one. So this equation is normalized wave function of a particle in one dimensional infinite potential well. Okay, This is the final topic, wave functions, probability densities and energy levels for particle in an infinite potential well. Here let us consider the most probable locations of the particle in the well. So first was for the infinite, next we will be considering for n is equal to 1, then n is equal to 2, then n is equal to 3. For 3 cases we have to derive. Okay, so in exam also if they ask you, you have to derive for 3 cases. So first case, n is equal to 1, it is in the ground state. In this case the equation will be written as follows, and if psi 1 is equal to 0, x is equal to 0 to a, then psi 1 is maximum when x is equal to a by 2. As you can observe, this is the maximum value. So the energy will be h square by 8 m square, n is equal to 1 in this case, that's why. So it is E naught. Moving on, n is equal to 2, just substitute the value of wherever you find n here as 2, and the maximum value here also it is x is equal to a by 4, and the negative value is 3a by 4. Okay, so substituting the values which we got here in the previous equation, what we get is E2 is equal to 4 E naught. Why we get 4? Because of n square. N is 2 here, so we get 4, and E naught is same as well as the previous one. Okay, so in the same way for 3 also, it will be 3 pi by a, and the maximum values are at 2a by 3 and a by 3. So what is the change that's happening here is the maximum value is getting changed here, as well as we get E3 is equal to 9 E naught. 9 how we got the same case, n square, n is equal to 3 here, so it will be 9, and E naught is same as previous one. Okay, so this is all what is there in the module 2 of 21PHY12, and thank you so much for watching. I'll see you in the next one.